Hello friends, you are welcome to my YouTube channel at GMAT41. In our previous practical physics class, I taught you how to carry out the experiment on the verification of Ohm's law. I explained to you how you can take your readings, because in that experiment we are required to measure the potential difference corresponding to the various resistance values presented as required in the instruction. In this video lesson, I shall present to you the table of readings, the table of values obtained, and of course we shall look at the graphical work, the graphical interpretation of that experiment, and of course make the necessary deductions from that graph as would be required by the instruction, as would be required in the instruction. If you are yet to watch the previous video lesson on the experimental verification of Ohm's law, please, I encourage you to do that so that as you follow along this particular video lesson, you will understand what the table of values and of course the graphical analysis we are going to deal with are based upon. Below this video lesson in the comment section and also in the descriptive section of this video lesson, I've decided to drop the link to the previous practical physics class so that you can watch the video lesson in order to be guided on what we are going to do in this present lesson. If you're yet to subscribe to my YouTube channel, please kindly do so, right? Subscribe to my channel. You can show more appreciation by clicking the like button, and of course, you can show more appreciation by liking this video and sharing this video to other friends and scholars so that they can watch and learn. Be assured that your comments are very well appreciated and welcomed. Let us get to business, alright? We are going to see first the table of readings. It's going to display on the screen. Please watch. Now you see that in the table of values presented in the screen, we have 4 columns. One is the column showing the resistance values used, alright, from 1 to 6. And of course, in the second column, we have the values of the potential difference obtained for different resistance values. So in that previous practical physics class, we actually took the reading from the voltmeter of the potential difference. We went ahead to evaluate the inverse of the resistance, which is 1 over R, and of course the inverse of the potential difference, which is 1 over V. Alright. Friends, based on this table of reading just displayed on the screen, we shall carry out the following instruction as required. We are going to plot a graph of the inverse of voltage against the inverse of resistance. Alright, the voltage potential difference, okay? We're going to plot a graph of 1 over V, or V raised to power minus 1, against 1 over R, or R raised to power minus 1. In plotting the graph, we shall see what the shape of the graph looks like. Alright? However, it is important that I state this, that this particular experiment follows this experimental theory and formula. 1 over V equal to R all over capital E. That R there is small r all over capital E multiplied by 1 over R plus 1 over E. This is the theoretical equation guiding the graph we are going to plot. And of course, this particular equation was what guided our experimental work in the previous practical class. Remember, like I stated, following the table of values obtained, we are going to plot the graph of 1 over V against 1 over R. Now, if you look at the multiplier of 1 over R, that R there is the external resistor, capital letter R, are you getting me right? If you look at the multiplier, the coefficient, it is R, small letter r. That small letter r is the internal resistance of the cell that we used, the battery that we used in carrying out the experiment in the previous practical class. Alright, so that small letter r represents the internal resistance And of course, the capital E there represents the electromotive force of the cell. Now you would recall that in our previous class, when we took the reading on the electromotive force, before ever closing the key and carrying out the full experiment, we obtained that the electromotive force of the cell used was 2.9 volts. And so there is something I need you to know. By the time we are done analyzing the graphical work on this experiment, I assure you that the electromotive force you are going to evaluate from that graph will be within the range of that 2.9 something, okay? Alright, the multiplier of 1 over r, because 1 over r is going to be plotted on the horizontal axis. What is multiplying it is small r, which is the internal resistance of the cell, all over capital E, that is the electromotive force of the cell. You observe that the mathematical sign before that small r over capital E is positive. And because it is positive, the graph we are going to obtain for this experiment, when we plot 1 over V against 1 over the external resistance, capital R, is going to be a positive graph. Alright, the graph will go this way. I hope you're following, right? The graph will go this way, and of course, it's going to have an intercept. It's going to have an intercept. The intercept, according to the theoretical equation guiding this experiment, is going to be 1 over capital E. That is to say, 1 over the electromotive force of the cell would give us the intercept of our graph. Alright, it is now time we are going to see the graph representing the table of value that was displayed on the screen a moment ago, and of course, interpreting or explaining all that was done in the experimental verification of Ohm's law. Please watch the screen as the graph of this experiment displays. You can see from the graph that 1 over V has been plotted against 1 over R. And you observe clearly from this graph that we've selected the scale, of course. On both axes, I used 2 centimeters to represent 0.2 units. 2 cm to represent 0.2 units. It simply means that each of the lines of the graph, are you following, has an equal division of 0.02. Each of the line in this graph sheet. So in plotting 1 over V against 1 over R, you can see that I did something on the vertical axis. Alright? You observe from the origin to that point of 0.4, you would see something like a zigzag line, okay? Now, whenever that is done in the graph, it means you are stretching the graph. And why do we do that at times? When the values you are to plot are so close together, okay, you can actually show that sign, which implies or means that you are stretching your graph. Now, I'm going to tell you more about that quickly. Please take a look and you see that the origin we have 0. Then after I introduced that zigzag sign, the next thing you saw at 2 centimeters above 0, above the origin, was 0.4. Now ordinarily, one may now think that the unit I selected on the vertical axis is every 2 centimeters equal to 0.4. But no, that is not the unit I selected. Because if you move upward after that 0.4 along the vertical axis, 1 over V axis, you notice that the next unit you saw in the next 2 centimeters is 0.6. And then when you move again, the next 2 centimeters is 0.8. When you move again, the next 2 centimeters is 1.0. So actually, on the vertical axis, I used 2 centimeters to represent 0.2 units. Observe, from 0.4 to 0.6 is 0.2 difference. From 0.6 to 0.8 is 0.2 difference. From 0.8 to 1.0 is 0.2 difference. So the idea of that zigzag created between the origin and 0.4 is simply to tell someone that this graph imaginarily is longer than what it appears to be. However, some values below 0.4 have been cut off. For example, instead of showing 0.2, that zigzag line shows that I had stretched the graph so that 0.2 had been cut off. So that 0.2 has been what? Cut off. So that 0.2 somehow is there by imagination. Alright? Okay, so that aside, if you want to learn more about stretching of graph in the case where you have clustered value, you can please contact GMAS41, are you following right, for more interaction. Let us move on and see the points, okay? That's the value of 1 over v corresponding to 1 over r will now be traced and they will be displayed on the screen on the graph. Please watch as these points are being traced. For each value of 1 over v, you have a corresponding value of 1 over r. Good. As this is done beautifully, you now have your line of best fit which goes this way. This is a wonderful graph. Very beautiful. I love it. I hope you do too. Okay, now we're going to proceed to see further information that we can obtain from this graph. The first, we are going to determine the slope of the graph. The slope, we shall use S to represent it. And how do we obtain the slope of the graph? Please watch as you see two lines, a horizontal and a vertical drawn. This horizontal and vertical will meet at 90 degrees. They are perpendicular to each other. And then both of them will touch the line of best fit. It's going to give us a right angle triangle as a shape. That is what we call our slope. I want to believe that from previous classes already you know how to take your slope. Good. You can see the slope there. And so we are going to evaluate the slope. Now how do we evaluate the slope? The formula for slope, you know, is change in the vertical axis over change in the what? Horizontal axis. That's to say, change in 1 over v axis all over change in 1 over r axis. So all we have to do for the vertical, you go to the vertical line of your slope, then trace from the starting point of the vertical line to the end point where it touched the line of best fit. You have to trace them to 1 over v axis, and of course you would get your values of final point of 1 over v minus initial point of 1 over v. You know, that's what we do in slope generally. y2 minus y1, which is the vertical. In this case, we plotted 1 over v on that vertical. All over x2 minus x1. So if you trace the vertical height of that slope, the initial point is going to give you 0.4, and the final point where the vertical line of the slope touched the line of best fit is going to give us 0.78. Then for the horizontal, which is the horizontal line of the slope, the starting point of the horizontal line of the slope and the end point. The starting point is where it touched the line of best fit, and the end point where it touched the perpendicular, that is where it touched the vertical line of the slope. If you take those 2 points and trace it to the horizontal axis 1 over resistance axis, you are going to get the initial point to be 0.04. And then the end point of the horizontal line of the slope, you have that value to be 0.8. And with this, you can calculate the value of our slope. Slope will simply be equal to 0.78 minus 0.4 all over 0.8 minus 0.04. Working this out, you get 0.34 all over 0.76. And once you divide that, the result you obtain as the slope is 0.45. So the slope of this graph is 0.45. The unit is ohms per volt. Ohms per volt. Alright, so that is that. Let us now take a look at the intercept of this graph. The intercept of this graph is simply the value measured from the origin to where the line of best fit cuts the vertical axis, the 1 over v axis. And if you take a look at this graph, you would see the point where the line of best fit cuts or touches the 1 over v axis. Now if you work in this, you're going to get the intercept measured from the origin to that point. You get it as 0.34. You get it as 0.34. So that's the value of the intercept. And the unit of the intercept is per volt. Per volt, or simply volt inverse. Is that okay? So we have the intercept C to be equal to 0.34 per volt. Okay, so we have obtained the slope and the intercept of this graph, which is based on the experimental verification of Ohm's law. Now, the next instruction we're going to carry out is to evaluate a quantity K. And that K is equal to S over C, where S is the slope and C the intercept. So how do we obtain the value of K? It's simple. We know our slope already to be 0.45 and we know our intercept to be 0.34. Slope is 0.45 ohms per volt and intercept is 0.34 per volt. And so, to obtain our K, following the formula S over C, we are going to write that K is equal to 0.45, which is the slope, divided by 0.34, which is the intercept. Evaluating that, we get this value of K to be 1.3. 1.3. And of course, the unit of K is ohms, because the divided slope by intercept. The unit of slope is ohms per volt, and the unit of intercept is per volt. So the per volt we cancel out, leaving us with ohms as the unit of K. So that quantity K is actually resistance. Is actually what? Resistance. But which of the resistance does it represent? Okay? In the instruction, we are required to state the physical significance of K. The physical significance of K. From the unit you obtain for K, it tells us that it is resistance. Then specifically, the resistance that K represents is internal resistance, not external resistance. That K there represents small letter r. Small letter r. Remember the theoretical equation guiding this experiment which I told you. Please, watch the board as I explain certain facts about this K. You recall that I told you the theoretical equation guiding this experiment is giving us 1 over V equal to small r, which is the internal resistance, over E multiplied by 1 over R and then plus 1 over E. Okay, now we were asked to evaluate K. K was given to be equal to slope over intercept. Now if you compare this equation given, the theoretical equation guiding our experiment, I plotted 1 over V against 1 over R. If you compare it with the equation of a straight line, you are going to get something like Y equal to mx plus C. This is what you're going to get. We've been doing this from previous graphical analysis in our practical physics class. You notice that 1 over V is the vertical axis, y-axis, as we plotted in the graph. You observe that 1 over R is our quantity plotted on the horizontal axis, x. Now from this equation of a straight line, this m multiplying x is your slope. Which simply means that small r, the internal resistance, divided by capital E, the electromotive force of the cell, which is multiplying the quantity we plotted on the horizontal axis, 1 over r. This small r over capital R is equal to m, your slope. Are you following, right? Therefore, the value of K we are asked to evaluate will simply be K. In place of slope, I can put R over E. And then we are dividing this by C. Now, continuing with your comparison, C is equal to 1 over E. That is 1 over the electromotive force of the cell. So in place of C, in this K formula, I'm going to put 1 over C. Now, if you take a look at this, this is 1 over E, not 1 over C, please. Okay, so in place of C, I am going to replace it with 1 over E because C is your intercept, 1 over E. If you simplify this equation now, this K, which is slope over intercept, is actually internal resistance divided by electromotive force all over, for the intercept, 1 over the electromotive force. Which if you simplify this, you get R all over E. You know, division of fraction, keep the numerator exactly like that, whether it is a fraction or not. Change this this division sign. Change this division sign to multiplication, and then inverse the denominator. This will be E over 1. You see clearly that the electromotive force will cancel out. Automatically, we are left with internal resistance divided by 1. Therefore, K is equal to the internal resistance of the cell. You can take a look at that. So this is actually how I got to know that yes, our K is resistance, no argument. But if I want to be more specific, this K is not the external resistance. Rather, it is the internal resistance, small r. So the physical significance of the value of K, or the physical significance of K as required in the instruction, is the internal resistance of the cell. I hope this makes sense, right? Okay, now we are going to proceed. One can actually still confirm that K is actually R here, since I told you that slope is R over E. Slope is R over E. You can get E from the intercept, since C is equal to 1 over E. How about I quickly do this analysis on the board so that you will see how these things link. I've proven that K is equal to the internal resistance. But we can also use the idea that slope is equal to internal resistance over electromotive force to still obtain that K value. Although this is not the direction that the instruction asked us to go. But you know, maybe in terms of exam, you can be asked to evaluate R from the slope. Okay, now let me show you that quickly. If you do that, our slope from the graph which you saw on the screen, are you following, right? I'm still going to present the graph anyway, but let's take a look at this. Slope which we obtained, remember our slope was 0.45, will be equal to R over E in comparison. R over E. So take note of this as equation 1. Then comparing again this equation of straight line and this theoretical equation guiding our experiment, our intercept, slope is S. Our intercept, C, is equal to 1 over E. So if I get my E, electromotive force, from the intercept, I can use it to obtain the internal resistance from the slope. And let us watch and see. Intercept, already we obtained it to be 0.34. Remember, we obtained intercept to be 0.34 in the unit of what? Per volt. So this is going to be 1 over E. Therefore, if you cross multiply, E will be equal to 1 over 0.34. And you know what? Evaluate this, and you will get that your E, the electromotive force of the cell obtained from the graph, is going to be 2.94. 2.94 volts. 1 over 0.34 give you 2.94 volts. This is interesting. Remember that I told you earlier that from the graphical analysis, we are going to actually establish the fact that the electromotive force of the cell we used is within the range of 2.9. And I remember that in our previous practical physics class, we measured that electromotive force of the cell using the voltmeter. We got 2.9 volts. After having run the experiment, are you following, right, and plotted the graph, you can see that by comparing and using value we obtained from the graph for intercept, the electromotive force gave us 2.94. If I'm to approximate this to one decimal place, you would get 2.9, which agrees with what we measured before we started this experiment. So we are actually experimentally correct and in line with what is expected theoretically. So having obtained our electromotive force, we can now use the value of electromotive force to calculate the internal resistance of the cell. We already know the slope from the graph. So watch this now. This will imply that using S equal to R over E, our slope, we obtained it from the graph as 0.45. And that will be equal to R over what? E. Our R we don't know, but E we have obtained it to be 2.94. If you work on this, cross multiply, and the internal resistance is going to be 0.45 times 2.94. The internal resistance will give us 1.3 ohms approximately, which agrees with the value of K that we obtained, because remember we got K to be slope over intercept, which gave us 1.3 ohms. So you can see actually why I told you that R and K, they are what? The same. So in responding to the question, what is the physical significance of K? K actually is the internal resistance of the cell. But based on what we've done already from the graph, we don't need to go through all this. I just have to show you this to prove that actually our K is internal resistance. using our theoretical equation that guides this experiment. Remember that the question could, or the instruction could follow this analysis I have done. Instead of telling you evaluate K equal to slope over intercept, you might just be asked, evaluate the electromotive force of the cell from the intercept, and also determine the internal resistance of the cell from the graph, okay? And of course, to get all these things from graph, from here, the electromotive force will be obtained from the intercept, and of course, the internal resistance from the what? Slope of the graph. This makes sense a lot. Let us proceed, please, in further things that the instruction requires that we obtain. Alright, in the next instruction, we are asked to carry out this calculation. So I have the question, I'm going to dictate it, alright? Two identical cells of EMF 3 volts delivers current to an external circuit of resistance 2 ohms. The internal resistance is 1 ohm. Find the current when the cells are in A, series, B, parallel. So for this question, all we need to do, we are asked to calculate the current. Is that okay? And now we have these two cells. The cells are identical. Each of them has voltage or EMF of 3 volts. Each of them has EMF of 3 volts. We have an external resistance there whose value is 2 ohms. And of course, the internal resistance of the cell, 1 ohm. Each of them will be 1 ohms internal resistance. So if we have this thing called EMF, E, we have E1 is equal to E2, and that is 3 volts. And then the internal resistance is we have R1 equal to R2, and that gives us 1 ohms. The external resistance of the circuit is 2 ohms according to the question. Alright, so what do we do here to get our current? The first part is we have to obtain the current when the cells are connected in series. For series connection, you should know that the electromotive force will have to be added. Okay, so we have that E is equal to E1 plus E2. That will give us 3 plus 3, which is equal to 6 volts. Then again, since these cells are arranged in series, the internal resistance will also be in what? Series. So you have to obtain the effective, the combined internal resistance of the cell in series. And when resistors are connected in series, simply add up the resistance values. And so we're going to have 1 plus 1, since each of them is 1 ohm, and that gives us 2 ohms. And of course, we can now calculate the current using the relationship that current is equal to the electromotive force divided by the internal resistance plus the external resistance. If we substitute here, this is going to give us 6 over 2 plus the external resistance is 2. 2 plus 2. And so the current here will give us 6 divided by 4. This is going to give us 6 over 4. And 6 over 4, what's going to be a value? So this is 1.5 ampere. That is the current when the cells are connected in what? Series. The second part of the question, we are required to calculate the current when the cells are connected in what? Parallel. Alright, now we need to understand the conditions for cells being connected in parallel. When cells are connected in parallel, you don't add up the electromotive force like this. You don't do that. In that case, for the fact that the cells are connected in parallel, number one, they would have the same value. Are you following, right? Just like in this case, the cells would be identical. So what is going to happen is that the total or the effective electromotive force will be any one of them. And like you observe, according to the question, each of them is 3 volts. So the total electromotive force will also be 3 volts. So take note, E equal to E1 equal to E2, and the value will be what? 3 volts. But then what about the resistance? That is the internal resistance. Take note, internal resistance is a property of the cell. It is the resistance to the flow of current as a result of chemical reactions taking place inside the cell. Just like the battery we use to carry out these experiments in verifying Ohm's law from our previous practical physics class, I told you something about internal resistance. The cells we have there are chemical reactions taking place in it. So this chemical reaction reduces the total EMF of this cell. I hope you're following, right? So what I'm trying to say in essence is that internal resistance is a property of what? The cell. Now, for the cells to be connected in parallel, it means that the internal resistance of the cells will also be in what? Parallel. So we want to get the total resistance value of this guy. The total internal resistance value. How do we do that? We don't just add them straight anymore. Are you following, right? When resistors are connected in parallel, the effective resistance is obtained using 1 over R, where the R is your internal resistance, small r, equal to 1 over R1 plus 1 over R2. It continues plus 1 over R3 depending on the number of cells that you have. So in this case, this is going to give us that 1 over R will be equal to 1 over R1 plus 1 over R2. And let me tell you one interesting thing. When we have just two resistors, you can simply obtain your R to be equal to R1 times R2 divided by R1 plus R2. If you simplify this using LCM, getting your effective resistance is just multiply the two resistance value and divide by the sum of the two resistance value. So this is going to give us 1 times 1 over 1 plus 1. Conclusively, we're going to have 1 over 2, which will give us 0.5 ohms. So this is the internal resistance of the cell when the cells are connected in parallel. That being the case, therefore, our current will be equal to, remember the formula connecting them, E over R plus capital R, okay? So we have our current to be, place of the electromotive force, we have 3, internal resistance 0.5, we are adding external resistance to it. We have only one external resistor here. Please do not go and resolve anything like adding up 2 plus 2, and maybe in this case of parallel, you do 1 over 2 plus 1 over 2. Don't do that. That capital R there is external resistance. Okay, it has nothing to do with the cell. So however the cell is connected does not have any effect on this external resistance as regards whether you need to add them or take reciprocal of the resistances and add. Just like we did for series connection in the case of internal resistance and parallel connection in the case of this internal resistance. You don't do that to this external resistance, please, because external resistance is not a property of the cell. So we have only one external resistance there, which is 2, and that's what we use in our calculation. So this will give us 3 over 2.5. So let us see what the current is going to be. This is 1.2 ampere. Good. So you see, in this case we have 1.5 ampere, and here we have what? 1.2 ampere. So this is the current that will be delivered in each case. Alright, the next thing we are going to look at is the precaution taken to ensure accurate results in this experiment. And of course, in that previous practical physics class, I mentioned this, alright? In the video lesson, I highlighted that. One of them is that you should ensure tight connections when running your experiment. Okay, this is to ensure that you get stable reading. You know, you are using a pointer instrument, voltmeter. So if the connections are tight, you know, it will help to avoid that movement. So the pointer will be stable before you take reading. And then again, you want to ensure that you open the key, maintain an open circuit after taking reading. Then of course, you should avoid error due to parallax. Meanwhile, for the second one, which I said you need to keep the key open after you have taken your reading, the reason is to ensure that the battery, the cell, does not run down quickly. Are you following while doing the experiment? Avoiding error of parallax, how do you do that? You want to ensure that you look straight on, okay, to the measuring instrument. In this case, the voltmeter we use. When you want to take reading, don't bend your head like this and watch from angle. Are you getting me right? If the pointer points this way, your eye should go in that direction straight. It should meet the pointer at 90 degrees, that's head on. Okay, so that is what you do to avoid error due to parallax. And of course, that's that for this particular experiment. I hope you enjoyed this video lesson. Please like and subscribe to my channel. and share this video lesson so that other scholars like you will benefit from it. I hope to see you in our next video lesson. But like I've always said, don't forget, from here at GMAS 41, there are a lot you can learn, not just in practical physics, but in other aspects of your science courses. I hope to see you in my next video lesson.